Okay, in this lecture we're going to continue our section 3.7 material on mechanical vibrations, that is modeling the motion of a mass spring system. And here we're going to consider the next case of motion for a mass spring system, which would be the case of damped free vibrations. So we know that in most applications, there will be some type of friction or damping force, which will affect the motion of our mass. So this force might be to some component within our system, or due to the medium that surrounds our system, things like air resistance. So if there is damping present, then the equation of motion for our mass can be given by my double prime plus by prime plus ky equals 0. So here we're still assuming free vibration, that is no external forcing being applied. So we have a homogeneous second order linear equation with constant coefficients. And we know to solve this, if we seek solutions of exponential form, we obtain a characteristic equation, which would be mr squared plus br plus k equals 0. And the roots of this characteristic equation are given by the quadratic formula, r equals negative b plus or minus the square root of b squared minus 4mk all over 2m. And as we've seen throughout chapter 3, the form of our general solution will depend on the nature of these roots, whether they are real distinct roots, complex conjugate roots, or real repeated roots. So in the case of a mass spring system, these three different types of roots correspond to different types of motion, and they're given different names. So the first case that we're going to consider is what is called underdamped motion, which corresponds to the case of complex conjugate roots. So if the expression under our square root for the roots, b squared minus 4mk, is less than 0, that is, if b squared is less than 4mk, so our damping coefficient b is relatively small compared to the mass and the stiffness of our spring, then the roots are complex conjugates. So here we would have something of the form, let's say R equals alpha plus or minus beta times I, where alpha would be the real part of our root given by negative b over 2m, and beta, the complex part of our root, well, if the expression under the square root b squared minus 4mk is negative, we could rewrite it as the square root of 4mk minus b squared times the square root of negative 1, which is I, over 2m. And in this case, the general solution, y of t, would be of the form c1 e to the alpha t cosine of beta t plus c2 e to the alpha t sine of beta t. Or we can rewrite this in terms of a single cosine function times an exponential, by making a change of variables as we did in the case of undamped free vibrations. So we could express this as some capital R e to the alpha t times cosine of beta t minus delta, where capital R would be given by the square root of c1 squared plus c2 squared, and tangent of delta is given by c2 over c1, so that delta could be found depending on the signs of c1 and c2. So looking at the general solution, we see that we're going to have oscillations occurring because of this cosine function. And since the value of alpha was negative b over 2m, which is definitely negative since b and m are positive constants, our solution, y of t, will approach zero. That is, our mass will return to its equilibrium position with oscillations. So our mass will pass through its equilibrium position several times. That is, our mass will continue to bounce back and forth through its equilibrium, but with decaying amplitude, eventually moving back towards its rest position or its equilibrium position. So here we would say that the mass oscillates with what we call quasi-frequency, denoted as beta. So whatever the argument of our sine cosine functions were, the imaginary part of our root r, and quasi-period denoted as capital T sub d, which is 2 pi divided by beta. So similar to the frequency or period of motion for undamped free vibrations, we call the quasi-frequency and quasi-period for this case of underdamped motion. So here this is known as underdamped because there is not a damping coefficient, B, that's sufficiently large to keep this mass from oscillating. That is, passing back and forth through its equilibrium position multiple times. Now the next case of motion that we'll consider is overdamped motion, and this corresponds to the case of distinct real roots. So if the expression under our square root, when we found the roots r, that is b squared minus 4mk, is positive, that is if our damping coefficient b squared is greater than 4mk, so damping coefficient is relatively large relative to the mass and stiffness, there are distinct real roots given by, let's call them R1, would be the negative b over 2m plus the square root of b squared minus 4mk over 2m. And R2 would be the negative b over 2m minus the square root of b squared minus 4mk over 2m. So real distinct roots, in which case our general solution, y of t, would take the form c1 e to the r1t plus c2 times e to the r2t. And here, since r1 and r2 are both negative, our solution, y of t, will approach 0. That is, our mass will return to its equilibrium position as time increases. And we don't have any oscillations occurring. So we can see this if we look at the expression for y of t. If I take this y of t expression, and let's say I factor out e to the r1t, where r1 is the larger of the two roots, then I'm left with c1 plus c2 e to the r2t. And so if I'm interested in whether this mass will pass through its equilibrium more than once, I could set this displacement expression equal to 0. And we find that there is at most one positive value of t, because we know this exponential term can't be 0. So depending on the constant c1 and c2, there's at most one positive value of time for which this expression in parentheses is equal to 0. So we can say the mass passes through its equilibrium at most once. That is, we do not see oscillations occurring. And now the last case of motion that we'll consider is called critically damped motion, which corresponds to the case of a repeated real root. So in the event that the expression under the square root, when we found r, that is b squared minus 4mk, is equal to 0, or if b squared is exactly equal to 4mk, then we have a repeated real root. Given by r1, which is equal to r2, is negative b over 2m. In which case our general solution, y of t, would have the form c1 times e to the r1t plus c2 times t e to the r1t. And here, since our root, r1, which was negative b over 2m, is less than 0, our solution, y of t, will approach 0 as time increases. That is, our mass will return to its equilibrium position. And then thinking about the motion here, we might be interested in whether this mass can pass through its equilibrium position more than once. So to determine that, do we possibly see oscillations occurring? Well, we can look at the form of our general solution, y of t. And if I factor out the exponential e to the r1t, I'm left with c1 plus c2 times t. So to see when our mass could pass through its equilibrium position, we would set this y of t equal to 0. And as with case 2, we know this exponential term can't be 0. And we see that depending on the values of c1 and c2, there's at most one positive value of t for which y of t could be 0. So we can say that the mass passes through its equilibrium at most once. That is, we do not see oscillations occurring. Okay. So now that we've discussed these different cases of motion for a mass spring system, let's look at an example modeling the motion of a mass spring system where there is damping present. So in this next example, we have a mass which weighs 16 pounds, and we're told that it stretches a spring by 3 inches. And this mass is attached to a viscous damper with a damping coefficient of 2 pound-seconds per foot. So if this mass is set in motion from its equilibrium position with a downward velocity of 3 inches per second, find its position y at any time t, and then determine the quasi-frequency and quasi-period. So as soon as we see reference to quasi-frequency and quasi-period, we know that we're talking about the case of underdamped motion. And then lastly, find the time tau such that the magnitude of our displacement, the absolute value of y, is less than 1/100th of an inch for all time t greater than that value tau. So as we did with our first example for a mass spring system, let's first agree on the unit of measurement for our displacement y. And here we see some quantities are given in inches, but our damping coefficient is in terms of feet. So let's maybe measure in feet here. Let us measure our displacement. In feet. Now, the equation of motion for this mass is given in general by my double prime plus by prime plus k times y is equal to 0, since there was no external forcing being described. And we're given in the problem statement the damping coefficient b and the weight of our mass. Now we know that weight is different from mass itself. So let's think about first how to find our mass. We'll say to find the mass m, we could take the weight of our mass and divide through by the acceleration due to gravity. So mass we know is force, or force is mass times acceleration. So mass would be the force acting on our mass, which is its weight, divided by acceleration due to gravity. And this gives us 16 pounds divided by, if we're measuring in feet, g would be 32 feet per second squared. So this leaves us with 1/2, where our unit for mass would be a slug here. So we have our mass m, we have the damping coefficient b. The next thing we need to find is the stiffness k. So to find our stiffness k, we can use Hooke's law. So our stiffness k would be equal to the spring force, which would be equivalent to the weight of our mass, divided by our initial displacement, y. So here we had a 16-pound mass, which stretched our spring by 3 inches. Now 3 inches, since we're measuring in feet, would be 1/4 of a foot. So we're left with a 64 pounds per foot for the stiffness of this spring. Again, that 1/4 of a foot is coming from 3 inches, or 1/4 of a foot. So we now have the equation of our motion given by m, which is 1/2 y double prime, plus b, the damping coefficient was 2, given in the problem statement, y prime, plus k, which is 64y, is equal to 0. Or in standard form, if we multiply by 2, y double prime plus 4y prime plus 128y equals 0. And then we compare this with initial conditions. So starting with our initial position, y of 0, we were told this mass was set in motion from its equilibrium. So our initial displacement is 0. And then y prime of 0, our initial velocity. Well, we were told a downward velocity of 3 inches per second, or 1/4 of a foot per second. And again, the downward displacement corresponds to a positive y, so a positive 1/4 here. So let's go about solving this initial value problem. We know that we would look for solutions of exponential form, y equals e to the rt power, so that r would satisfy the characteristic equation, r squared plus 4r plus 128 is equal to 0. And we could then solve for r using the quadratic formula. R would be -4 plus or minus the square root of 4 squared, or 16, minus 4 times 1 times 128, which leaves us 512, all over 2 times 1. So this gives us a -4 plus or minus, after we simplify a little, we have 4 root 31 times I over 2. So dividing through by 2, we get -2 plus or minus 2 root 31 I. So we have the case of complex conjugate roots, which means that our general solution, y of t, would have the form c1 e to the -2t cosine of 2 root 31t plus c2 e to the -2t sine of 2 root 31t. And then we need to find our derivative of this general solution to apply the initial conditions. So for y prime, by the product and chain rules, we get negative 2c1 e to the negative 2t cosine of 2 root 31t minus 2 root 31 c1 e to the negative 2t sine of 2 root 31t minus 2c2 e to the negative 2t sine of 2 root 31t plus 2 root 31 c2 e to the negative 2t cosine of 2 root 31t. So once I have my general solution and its derivative, I'm ready to apply my initial conditions. So let's look first at y at time 0. So y at time 0 leaves us c1, which was equal to 0 since our mass was starting at its equilibrium position, and y prime at time 0 gives us negative 2c1 plus 2 root 31 c2, which we were told had to equal 1/4. Now, since c1 is equal to 0, this first term is 0, and it follows that c2 would be 1 over 8 root 31. And so substituting back into our general solution, y of t would be c1, which was 0, plus c2, or 1 over 8 root 31, e to the negative 2t sine of 2 root 31t, where we were measuring in feet. So y of t denotes our displacement in feet from the equilibrium position after t seconds. Now, we were also asked to identify the quasi-frequency and quasi-period for the motion of our mass. So here the quasi-frequency is what we call beta, which would be 2 root 31. And the quasi-period, which we denote as capital T sub d, is 2 pi divided by beta, which leaves us with pi over root 31. Now, the last thing that we were asked to determine was the time tau such that the magnitude of our displacement, that is the absolute value of y, was less than 1/100th of an inch. So let's take a look at this. Let me say to determine the value tau such that the magnitude of our displacement is less than 1/100th of an inch. Let's take the magnitude of our displacement, y of t. So that is the magnitude of 1 over 8 root 31 e to the negative 2t sine of 2 root 31t, which would be equal to 1 over 8 root 31 e to the negative 2t, since these terms are all positive, times the absolute value of sine, 2 root 31t. And since I know the values of sine oscillate between positive or negative 1, the largest magnitude that I could have for this sine function would be 1. So the magnitude of my displacement always has to be less than or equal to 1 over 8 root 31 e to the negative 2t. And I want to make sure that this maximum value for my magnitude is less than 1/100th of an inch. Now again, we were measuring in feet here. So this 1/100th of an inch would be equivalent to 1 over 1200 feet. So we're going to make sure this is less than 1 over 1200. And let's solve this inequality for t. It means that e to the negative 2t would have to be less than 8 root 31 over 1200. Or dividing through by 8, that leaves us root 31 over 150. So taking the reciprocal of both sides, e to the positive 2t has to be greater than 150 over root 31. And therefore 2t is greater than the natural log of 150 over root 31. And so finally t has to be greater than 1/2 the natural log of 150 over root 31. Now, making use of a calculator, we can find that this value is approximately 1.65, where we were measuring in seconds. So this would be our value for tau. This is the time at which the magnitude of our oscillations is within 1/100th of an inch from our equilibrium position.